Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to explore improved Euler's method. It's a continuation of a series of videos for students in differential equations who are going through numerical methods for approximating solutions to differential equations. You should have already watched my video on an introduction to numerical methods, and then my second video, which was about Euler's method. And now we're going to go into improved Euler's method. The difference between this video and the last is that in this video, I will not be doing anything by hand because improved Euler's is a heavy technique, a little bit heavier than in Euler's method, and not one that you want to do necessarily by hand too much. All right, just like the Euler's method video, we're going to start with a slope field. If you need to review what a slope field is, go watch my previous video. Also note, we still have the same good old solution curve in the background. So our initial condition for this will be at x sub 0, y sub 0. And our background function will be y prime is equal to f of x comma y. So a first order differential equation. Just like last time, we're going to create a lineal element at x sub 0, y sub 0. And we're going to use that lineal element to target a value ahead. So let me turn off the slope field because that's just going to get in our way. And one thing I will do here is I will go ahead and just start listing out the steps for improved Euler's method. Just like last time, we have to compute the slope of the lineal element at x sub I, y sub I. So in this first case, we've computed the slope of this lineal element at x sub 0, y sub 0. It's the initial condition, so they handed us those values, so it's easy to plug into our derivative function or differential equation, y prime. Notice the notation that's being used here. By the way, this notation I just used because I dislike the notation that most authors use. They use a k sub 1i or something like that. I like m sub 1i because that to me sounds like slope. And just like we did with Euler's method, we're going to extend that lineal element that you see right here, and we're just going to fire forward until we get h units ahead. So let me go ahead and show that. So this is us firing forward until we land at this point. But the difference between Euler's method, which we saw previously, and improved Euler's method is that that point we land at is not going to be our approximation to y of x sub 1. Instead, we put our brains to the test and think, well, could we make that a little bit better? And the answer is, yeah, we sure could. What if we were to find the slope of the lineal element right there? Now you may say, well, didn't we do that in Euler's method before? And how is that different in this case? Well, instead of using the lineal element here to fire to our next guess, let's actually grab that lineal element. Let's drag it back to where we started firing from right here. And we'll take the average of the two slopes here. So again, we have a slope at f of x sub 0, y sub 0 in this case. And then we also have a slope at x sub I plus 1, which is basically our next value, comma y sub I plus h m sub 1i. Now what the heck does that mean? If you just read this from improved Euler's method algorithm, it means nothing to you. But really what that's saying is, I'm going to take the slope at the lineal element we're standing at, that's what m sub 1i is, and then I'm going to fire forward until I reach this next point, and I'm going to find the slope of that. And that's what m sub 2i is. It's f of x sub, let's just pretend we're at, looking at x naught here. So that's f of x1, that does make sense, that's the x value there, comma, y sub 0, this height right here, plus h times the slope of this extended lineal element here. In other words, it's the slope at this point. That's the slope of the lineal element at this point. By the way, if you don't believe me that that's the slope of the lineal element there, you can see in the background that that slope definitely looks like what the slope field should look like right there. Now, like I said, we drag that all the way back here. And our idea is to then average those two and fire forward from the average of those two slopes and look at what a better approximation to y of x sub 1 that is. Remember, with Euler's original method, our approximation to y of x sub 1 was right here. But by taking the average of the slopes at x0, y0, and x1, y1, we get a little bit better approximation. And by the way, this is how most numerical methods are built. You start thinking about, well, how can I target a little bit better? Note, again, that's the error right there. Very small error. Now, like I said, what you're gonna do with these two slopes that you just computed, you compute their average. So your next y value in line, which we just showcased right here, is just your old y value, y0, plus the average of the slopes of those two lineal elements times h. It's in a way somewhat similar to Euler's original method, but because you're averaging slopes, your error begins to reduce. So just to remind you, this lineal element or extended lineal element is the average of the slopes at x sub 0, y sub 0, and the slope at not x sub 1, y sub 1, but where the lineal element extended to here. So that would be the other slope we averaged out, and you average those two, that's what this is. And that gets you to this point right there. Now I'll turn that off. And just to repeat the process, you find the slope of the lineal element at x sub 1, y sub 1. You extend that lineal element a step size of h to get to your x sub 2 location. Of course, you take a firing shot out there. There you go, fire all the way up there. But remember, that's not actually what our approximation is going to be. It's just that that's one slope we're going to consider. Remember, we need to average slopes. So where that point landed at x sub 2, whatever the y value is there, we're going to find the slope of the lineal element right there. And you can see the slope field, that lineal element should have a positive slope, but almost flat. And there you can see it. Now, what do you do with the slope of this first lineal element and that second lineal element? Well, you can see it right here. You're going to average them. So let me bring that second lineal element back. And we'll go ahead and average those two slopes to create a brand new line. And where that line points will be my next guess. Now you are probably saying, well, hold on a second. I could see the error would have been less had we stopped at this point right up here. And you're absolutely right. But improved Euler's does not look for when error is minimized. It just is an algorithm. That's all it does. So the entire algorithm is listed right here. We let m sub 1i equal f of x sub I, y sub I. We let m sub 2i, our second slope, to be f of x sub I plus 1. That is also known as f of x sub I plus h, comma, y sub I plus h m sub 1. And then using those two computations, we'll average them out, multiply them by h, and add those to the last y value to get to the next y value. Let's go ahead and see this in action. So what you're seeing here is our previous work with with Euler's method. So I saved the table there. I actually hid, if you see these letters, skip the letter D, I just hid the computational cells there just because I didn't want it in our way. Because this gives us all the information we need to compare methods. So remember, our original Euler's method, we had a step size of 0.1. So I'm going to go ahead and go back here where I say h equals, and I'm going to change that out to 0.1. Now, if you're a fan of using Excel, which I think is always a nice thing, then let me show you another little trick. If you don't want that h equals in the way, and instead, if you're just okay with knowing that that's h, you can click on the cell and then click up here. This is the name of that cell. It's called N1. Well, I can just call it H. And from this point forward, I hit enter after calling it H. From this point forward, I go back through all of my computations where they say N1, and I trade those out for H's. So watch what happens when I just do that. Remember, the trick was to double click the lower right hand corner of a cell. It will extend that pattern all the way down. As long as there's something on the left, it'll extend the pattern all the way down. So now if I click in any of these cells, it's just taking the previous cell plus H. And remember, H is the name of the cell way over here, that guy right there. And I'm just going to do that. Not that it'll change any thing for us in this process, but I'm going to do that for all of the cells that contained that computation. I think it was only this one hidden cell right here. So notice this hidden cell had an h f of x sub I y sub I. So in that cell, I see the n, the $n $1. I'm going to replace that with just h. Not that I have to. Again, no biggie. But I'm going to double click the lower right hand corner, extends it down, and now I'll just go ahead and re-hide that cell. I don't need it in my way. All right, that's a little trick, and I'm a big fan of showing like little Excel tricks. So I wanted to keep all that information because we're going to need it, but now we're going to also build improved Euler's method. Now, taking a cue from Euler's method, I had I, x sub I, and y sub I. And remember, x sub I is not going to change, so I'm not going to create a column for that. But y sub i's, they're definitely going to change. So I'll create a column for y sub I. Remember, this is new column is for the improved Euler's method. I'm going to leave a little space there. Actually, no, I'm going to call it e sub I. And the only reason why I'm putting that there is because I want to take a look at the error later on. So I just want those next to each other. No biggie. And we happen to know that our initial value for y sub 0, because this is about I equals 0, so x sub 0 was 1, y sub 0 was also 1. That was our initial condition. Now we had a formula for m sub 1i and m sub 2i. Let's go ahead and take a look at those. This is back on the Desmos screen right here. You can see I was hiding all this stuff from you as I was doing all my computations, but that was the code in the background that I was fiddling with. Anyway, m sub 1i is just f of x sub I, y sub I. So let's go ahead and do that. Again, this is going to equal our function f, which is what y prime is equal to, evaluated at x sub I, y sub I. Well, our function in this case, remember, was y prime is equal to 2xy. So this is going to be 2 times x sub I, which is right here, times y sub I, which is right here. That's the y sub I want, right? Because it's for Euler's method. Or improved Euler, sorry. I don't want to use the y sub I from Euler's method. I want it from improved Euler's. I'll hit enter. The next thing I'm going to need is m sub 2i. And going back and looking at our Desmos applet, we can see that m sub 2i is going to be f evaluated at the next x value in line, comma, the current y value plus h times what we just computed for m sub 1. Let me say that again. M sub 2i is going to equal the next x value in line. The next x value is this 1.1. However, it actually is not to my benefit to point there. I'm just going to say it's our current x value plus h, because that's what the next x value is going to be. Now remember, it's actually our f evaluated at that, so I have to remember that f is 2 times x times y, sorry. So it's 2 times, and then the quantity of whatever that x value is. It's x, the next x value, which is 1.1. And then we're going to multiply that by our current y value. And notice how I'm going to use parentheses, because our current, it's a group of information that we're doing here. So it's our current y value plus h times what we just computed right here. And every once in a while, Excel does this weird thing where you can't click in the cell because you've bled into it. If that's the case, just note this is column J, row 2. So it's J2. I'm just going to type in J2 there. And so that's what m sub 2i is. Now, if it doesn't show a lot of digits there, just know that Excel is actually saving all that information. And now that we've computed m sub 1i and m sub 2i, well, going back to Desmos, we can see the next y value is just the previous y value plus the average of those two slope functions we just computed, m sub 1i and m sub 2i, all multiplied by h. So again, the next y value is going to equal the previous y value plus h, I'm going to write it that way, times the average. And remember, in Excel does not do implicit multiplication. So if I type h and then start a parenthesis, it doesn't know what that means. So I have to say plus h times the average. So h times, and I'm going to average up m sub 1 and m sub 2. So m sub 1 plus m sub 2. And the average means take that sum and divide by 2. I'll hit enter, and that's my y sub 1. Now that I have that started, I'll just drag that down. If I tried to double click, by the way, the lower right hand corner, it would go nowhere because that double click trick needs something directly to the left of it. It needs a pattern to the left to be able to autofill all the way down. So you'll see that issue right here. I can't double click the lower right hand corner. I just tried. So I have to drag this down. But what I can do is now that I have a full column here, I could double click the lower right hand corner of this and it'll autofill. Now what you see before you is just a bunch of numbers. It looks pretty ugly, doesn't it? So let's go ahead and do what we did last time. Increase the number of decimal places we see. So I'll decrease it down so I could start here. That's 1, and that's 9 decimal places of accuracy that I can see. Obviously it holds more decimal places than that. And then the error, remember, is equal to the absolute value difference between the real y at x sub I minus our approximated y value at x sub I. And again, you can just go ahead and double click the lower right hand corner and it'll autofill. Now I want to draw your attention to something here. We wanted to approximate y at 1.5. So at x equals 1.5, the true value for our solution is 3.49 and change. Using Euler's original method, well, we got close, but really not great. Using improved Euler's, on the other hand, the error is 0.03. It's 4/100ths is the error versus 0.56. That's more than 10 times the amount of error. So improved Euler's obviously is a much better scheme. And it gets even better if I decide to increase the number or the step size, or decrease the step size, I should say. So let's say that instead of h being 0.1, I want h to be 0.05. So in other words, I'm going to take steps of size 0.05 to get to x equals 1.5 from x equals 1. When I do that, you see everything adjusts. Let's find x equals 1.5. It's right here. The error, again, this is the column for the error right here for Euler's, is 3/10. The error for improved Euler's is 1/100th. So much better. Now we've been talking about stepping only a half a unit away from our initial condition. The error does grow. If you look at Euler's method, well, approximating y of 2 using Euler's method gives me a pretty significant error, 4.5. I'm that many units away from the true value of y of 2 using Euler's method. But Euler's improved method, I'm only 2/10 off. It does require a little more computation. You have 2 of these computations versus just a single one that I've hidden right here. We had that one computation versus the 2 computations, M1 and M2 there. If you're taking or going to be a computer science major, then you know me saying that's 1 computation versus 2 is not actually correct, because this 1 computation actually is 4 computations. It's 2 times x times y, actually 3 computations, right? 2 times x times y times h. So that's 3 computations. However, this m sub 1 I is 2 computations, 2 times x times y. This m sub 2i is a bunch of computations actually. It's 2 times x plus h times y plus h times m sub 1. And that's more computations. Then you have to add those 2 values up. Then you have to divide that by 2. Then you have to multiply that by h. Then you have to add that to y sub I. So there are more computations here. However, if you're willing to suffer those extra computations, you get better approximations. Now what I've done here is I've just hid the columns that we're not really that interested in. And then I just labeled the methods because we're going to use this style again for Runge-Kutta. All right, but that does it for improved Euler's. Notice I did not do this or any computations on this by hand, mainly because, well, you don't want to do this by hand if you can avoid it. You want to use some type of computational technology. So get used to using computational technology. There's nothing wrong with it. Numerical methods are not always the best. In fact, they're almost often the last resort, but unfortunately, they're also used quite a bit because we can't find analytic solutions to first order differential equations easily. Actually, to any differential equation very easily. So we often have to resort to numerical methods. That being said, I'll see you in the next video where we're going to go into the Runge-Kutta method.